Hello everybody, getting ready to lesson 2.7 part 1 of pre-calculus math today. Email me here for course materials, tutoring, etc. 2.7 part 1, we got 50 points here of classwork today. You have 0 points in your notebook taking. So teachers, bell work for today. In these two exercises, simplify, have your students simplify these expressions. Give your students 3-4 minutes for that. Okay, welcome back for today's solutions of your bell work. X over 8, quantity to the negative 3 power, and then 4x squared, all of that to the negative 2 power. So how would we do that, students? Well, for up here, you have a negative exponent, so you know you're going to reciprocate your quantity inside the parentheses. So when you reciprocate and then cube it, you have 512 over x cubed. And then for 4x squared to the negative 2 power, again, you reciprocate here, 4x squared. And then when you square everything in here, you come up with 1 over 16x to the 4th power for that. Okay, into our first page here, students. This is in your class worksheet. The graph of a rational function. To sketch the graph of a rational function, use the following guidelines. Let f of x equals n of x and over d of x. So what does n of x be? Where n of x and d of x are polynomials. And number 1, simplify f if possible. So any restrictions on the domain of f not in the simplified function should be listed. So basically this is your numerator, and then this is your denominator here, where both these n of x, or numerator and denominator, are polynomials. Simplify it if possible. If you can factor, go ahead and do that. And then 2, find and plot the y-intercept, if any, by evaluating f of 0. So let x equal 0, then see if you have any y-intercepts. After you try that, find the zeros of the numerator, if any, by setting the numerator equal to 0, then plot the corresponding x-intercepts. So your x-intercepts will be the zeros of your numerator. And then number 4, find the zeros of the denominator, if any, by setting the denominator equal to 0. Then sketch the corresponding vertical asymptotes using dashed vertical lines, and then plot the corresponding holes using open circles in your lines, in your graphs. So the zeros of the numerator, which will be your x-intercepts, and then the zeros of the denominator are your vertical asymptotes. 5, find and sketch any other asymptotes of the graph using dashed lines. 6, plot at least one point between and one point beyond each x-intercept and vertical asymptote. 7, use smooth curves to complete the graph between and beyond the vertical asymptotes, excluding any points where f is not defined. So here's kind of like your list here of strategies of plotting rational functions. The simplest type of rational function is the parent rational function, f of x equals 1 over x, also known as the reciprocal function. The basic characteristics of the parent rational function are summarized below. So the graph of f of x equals 1 over x, here is that graph here, f of x equals 1 over x. So your vertical asymptote will be your x-axis, and then your your y-axis would be your vertical asymptote, and then your horizontal asymptote would be your x-axis here, and your curve here will be decreasing, and then this will be decreasing here as well. Okay, so the domain will be the for x, it will be negative infinity to 0. That would be your domain, because when x equals 0, that's your y-axis here, and these graphs coming from this direction, will not cross the y-axis. along with 0 to infinity. And again here, this part of the function will use the y-axis as an asymptote, and then it will continue in this direction to infinity for the domain. And then the range will be negative infinity 0. So the range here will be negative infinity to 0. This will be your y, your range of this side of the function here. It will start from negative infinity way down here and then come up to 0, almost 0. And then over here on this side, it'll start at 0 and it will go to positive infinity for your range. And then there's no intercepts here, and there's no intercepts. And it's decreasing on the negative infinity to 0. So, and also from 0 to infinity. So from negative infinity to 0, it's decreasing. Both these sides of the graph are decreasing. And then the symmetry is in the origin here. Both of these are symmetrical in respect to the origin. And then again here, your vertical asymptote is your y-axis. Your horizontal asymptote is your x-axis. Vertical asymptote y-axis, and horizontal asymptote is your x-axis. Let's go into an example. Example 1, library of parent functions, f of x equals 1 over x. Sketch the graph of the function and describe how the graph is related to the graph of f of x equals 1 over x. So g of x equals negative 1 over x plus 2. So a, with respect to the graph of f of x equals 1 over x, the graph of g is obtained by reflection in the y-axis and a horizontal shift 2 units to the left as shown. So right here is g of x equals negative 1 over x plus 2. So here is g of x equals negative 1 over x plus 2 right here. And it's also over here as well. This is part of g of x equals negative 1 over x plus 2. It's this side over here, and then it's this side over here. And it's shifted to the left because of this down here. Your zeros down here would be x equals negative 2 would be your vertical asymptote here. And then your x-axis is your horizontal asymptote. So shift 2 units to the left here at negative 2. What else can we find out about it? So here, why don't we get a second situation here? H of x equals 1 over x minus 1 plus 3. So with respect to the graph of f of x equals 1 over x, the graph of h is obtained by horizontal shift 1 unit to the right and a vertical shift 3 units upwards. So we have our 3 here. This serves as a vertical shift. And then we're going 1 unit to the right here to so f of x equals 1 over x, that's the upper part, and then this is the lower part of f of x equals 1 over x. And then this is everything's shifted up here 3 units. So we're when x equals or rather y equals 3, this is your horizontal asymptote up here, y equals 3. And then we shift to the right 1 unit. So here is our vertical asymptote at x equals 1. That's our vertical asymptote. So 1 unit to the right and vertical shift 3 units upwards here. So y equals 3 is your horizontal asymptote. Okay, let's try one. Sketch the graph of the function g of x, and describe how the graph is related to the graph of f of x equals 1 over x. Students, this is yours down here. Do the same thing down here. This is your explanation box here. So let's try number 5 here. The graph of g equals, 1 over x minus 4 is a horizontal shift of 4 units. So we got that. We have a horizontal shift of 4 units. And then to the right of the graph of f of x equals 1 over x. So here's our shift here of 4 units. So here is our vertical asymptote here at x equals 4. Then here is f of x equals 1 over x here. That's our parent. And then this is our child here. So it shifts to the right 4 units, and it basically does the same thing. It's decreasing on both sides, has basically the same symmetry as 1 over x. Example 2, sketching a graph of rational functions. Sketch a graph of g of x equals 3 over x minus 2 by hand. So y-intercept, so 0, negative 3 over 2, because g of 0 equals negative 3 over 2. So when x equals 0, y would equal 3 over negative 2. So there is your y-intercept there. Okay, the x-intercept, none, because 3 cannot equal 0, so there is no x-intercept. Vertical asymptote is x equals 2, because that is a 0 of the denominator. So here's our vertical asymptote here. And then the horizontal asymptote, y equals 0, because degree of n of x, your numerator, your degree up here, is 0, actually. There is no degree up here. And then the degree of d of x would be 1 here. So the degree of n of x is less than the degree of d of x. There is no variable up here with a degree. So, knowing that information, here are your asymptotes, here's your y-intercept. You know that much. So g of x equals 3 over x minus 2. So again, there's our vertical asymptote. Here are our points here. So when x equals 3, y equals 3. When x equals 5, y equals 1. So here we can plot these here. When x equals negative 4, y equals negative 0.5. That'd be right here. And then when x equals 1, y would equal negative 3. And then when x equals 3, y equals 3. And then when x equals 5, y equals 1. So, and then when x equals 2, it's undefined because that's your vertical asymptote. So you can see what's happening here with this. I mean, the curves are going to go like that, right? So by plotting intercept asymptotes, a few additional points, you're going to obtain the graph shown. So here is a more accurate representation of this function here, right here. So your horizontal asymptote would be y equals 0. And your vertical asymptote is when x equals 2 from here. And we get our horizontal asymptote because the degree of n is less than the degree of d. So confirm this with a graphing calculator, and of course you will. Let's go into our example now. Sketching the graph of a rational function here. We're going to sketch this, and then y-intercept, x-intercept, vertical, and the horizontal asymptote. So to do that, and then additional points we're going to throw in there. So our y-intercept, when x equals 0, y equals 1/2. Then the x-intercept, there is none. There is no x-intercept. Then the vertical asymptote is x equals 2. Our zeros down here will be at x equals negative 2. And then horizontal asymptote is y equals 0, because again we have the degree of n is less than the degree of d. So when x equals 0, y equals 1/2, we can have that. So we know this much here. Here's our vertical asymptote at x equals -2. Here's our horizontal asymptote at y equals 0. Then what's that? And then we just continue to plot here points to make up this part of our function. And then down here, this is our other part of our function. Once you plot up here, your points to fill in this. So there is this side of the function, and then there is your curve on the other side of the function. For plotting these points here. So when x equals, what is 1, 2, 3, 4, 5, when x equals 6, y equals 1/8, etc. like that. Then on the other side here, when x equals, say, -1.5, it makes this number way bigger, so that's why it shoots up here along your vertical asymptote. And here is your actual plot here. This is what it would look like on your graphing calculator. So we have a y-intercept here at 0, 1/2. So you just take it from there. Okay, finishing that. Now remember that the graph of G in example 2 is a vertical stretch and a right shift. So here is G of x equals 3 over x minus 2. So we have a vertical stretch and a right shift of the graph of f of x equals 1 over x. So a vertical stretch here would be that the curve kind of distances itself here from where the vertical asymptote crosses the x-axis. There's more distance here than there was from the other, the parent here, 1 over x. And so and then we have a right shift. We have a right shift here because of x equals 2. So vertical asymptote is x equals 2. That makes your 0 here. So that makes your shift here to the right of 2. Because g of x equals 3 over x minus 2 equals 3 times the 1 over x minus 2, which equals 3f of x minus 2. This is the analytical way of looking at why there is a vertical shift here. Is you have a factor here of 3 where it explains the distance here. It triples the distance between where this intersection is to the actual curve because of your 3f. So let's get into that further. So sketching the graph of rational functions, sketch the graph of f of x equals 2x minus 1 over x by hand. So the y-intercept, none, because x equals 0 is not in the domain of the function. When x equals 0, it makes it undefinable. So the x-intercept is 1/2 0. So because 2x minus 1 equals 0 when x equals 1/2. So this is your x-intercept here at 1/2. So when x equals 1/2, y would equal 0. So that would be your x-intercept here. There's no y-intercept. So the vertical asymptote is x equals 0. This is 0 of the denominator when x equals 0. So there is your vertical asymptote. Then your horizontal asymptote is y equals 2 because the degree of n equals the degree of x. So that would make this your horizontal asymptote here. Your coefficient of your variable here would be your horizontal asymptote there. And then additional points, here's your table that you can use to plot additional points to sketch it in. So here is our function here, 2x minus 1 over x. And see the distance between here, your intersection here, and your y-axis, where where your vertical asymptote and your horizontal asymptote intersect, and then the distance between there and the actual curve is not the same as it would be if this was a 3. That would make it further out here. So anyway, y equals 2 is an asymptote, and then vertical asymptote is x equals 0, which is the y-axis. And then you plot these other points, so you will go ahead and plot those. Okay, let's try another one here. Sketching the graph of this thing here, 1 minus 2t over t. So let's do this. Okay, so solving our number 5 here. F of t equals 1 minus 2t over t. So immediately here, the degree here is the same. So we know our horizontal asymptote will be our coefficient here of t in the numerator, which is -2. So we know our horizontal asymptote will be -2 for this one. And then here's the table of values. Our x-intercept will be 1/2. Why is that? Because that'll be a 0 of the numerator. When t equals 1/2, f of t will equal 0. So we can see that will be our x-intercept, our t-intercept there. So our y-intercept, we have none. Now our x-intercept here will be the same thing as our t. We have no y-intercept here because when t equals 0, it's not defined at that. So when t equals 1/2 now, our y will equal 0. So here would be our t-intercept there. And then y equals -2 again because the degrees here are the same. So we go to the coefficient, which is -2. So that'll be a horizontal asymptote down there. Then our vertical asymptote, since the degrees are the same, our vertical asymptote will be the y-axis here. So having all of that information, these are what your curves will look like here. So again, here is our t-intercept will be 1/2 and then 0, and then our curves will be like that. And then here's your horizontal asymptote at y equals -2.